Okay, welcome back, everybody. First thing is I want to apologize. I couldn't make it to my office hour today. So if you have planned to come by, my apologies. You can, if you want, after my class tomorrow at 4 o'clock. Feel free to drop by then. Okay. Um. Okay. Any questions? Down. Let me get. Oh, this picture behind me, I spent 40 years looking for it. I found it a couple of days ago. That's me 100 years ago. It took a long time to find it. Anyway, what I want to do is go to the course website for a second. I want to go into the simulation that I showed you or told you about way back in the beginning of the semester. Just to remind you, and this simulation will help you before we go back to chapter 5. This will help you to hopefully get a picture of the atom and how it's put together, okay? With respect to the proton, neutrons, and electrons. So under the modules, there is a module. Oh, one additional item before I forget. I did send out a survey, and I did get a few people who did complete it, and I appreciate that. But thank you for the feedback. If you haven't had a chance to do it, please go in there and answer the questions. I guess there's an issue with respect to the volume of Zoom. I think I took care of the issue from my end because I was using the microphone off of my camera, and which is kind of far away from I speak. So I corrected that to make sure I got the speaker off the system. So that should take care of that. I got the volume maxed out. I'll speak up a little bit louder and make sure that things get heard. And if there is a problem with you hearing me, please let me know, and I will see what else I can do. Sounds a lot better. Okay. And it's probably because I did have my webcam speaker on, which is, like I said, about 1.5 feet away from me. So I'm glad it does sound better for you. Okay, so that put aside, on the course website under the modules, right underneath the welcome and syllabus, there's an additional chemistry resource module. Okay, everybody can see that? You know, make sure I'm sharing that screen. All right. So you see a couple of simulations that we can use. You can use throughout the semester to help you with some aspects about topics we want to talk about. I'm going to select build an atom. Okay. And it will activate the simulation, which was created by, I believe, University of Colorado. So you can select the atom. I would go with the symbol. Okay. And the game part is pretty good too. It kind of, if you run through it, kind of, once you become familiar with protons, neutrons, electrons, that game part will kind of, it's like a study guide for you. So give that a shot. So with the symbol choice, you'll see here, I have on the far right will be where the symbol and the atomic notation, which, by the way, the additional information is I sent prepared an announcement about the atomic notation. There's a question in your homework that gives you choices of different atomic notations, and you're supposed to select which one is correct. And I go through some points about atomic notation and the format, so you can discern which one is correct with respect to the question. All right, so I got 3 buckets here, buckets of protons, neutrons, and electrons. Okay, I'm also going to click stable, unstable, because once an atom is stable, unstable, it would start to vibrate. I'll show you here in a second. Now, if I grab a proton and put it near let me back it up. In the center here, you see three marks or three energy levels, dotted lines, circles, and then the X, which represents where the nucleus will be. The dotted lines represent the different energy levels, specifically only the first two, energy level 1 and 2. So if I grab a proton and I just put it anywhere near the dotted lines, it automatically goes to the center because that's where protons exist. Notice by adding a proton, I created the element hydrogen, okay? And repeat again, if I grab another proton, I create helium, okay? And 3 is lithium, okay? So as we stated before, the proton defines what that element is, okay? Now we got hydrogen element number 1, meaning it's got 1 proton and 1 electron. So if I grab the blue, which are the electrons, bring it in anywhere in the center, for example, and it would automatically go out to the first energy level because our motto is protons in the center, nucleus, and the electrons orbiting, okay? Specifically orbiting and in specific energy levels, and even more so in specific what we call sublevels or orbits. All right, so that is hydrogen, and the symbol to the right, you got the letter H, okay? You see the atomic number is 1, it's got 1 proton and 1 electron, okay? Now, when I select a neutron, it goes to the center, and the number goes up to 2, okay? That's the isotope. There's 3 isotopes. There's hydrogen 1, hydrogen 2, hydrogen 3. Hydrogen 1 has no neutrons. Hydrogen 2 has 1 neutron. And hydrogen 3, as you can see, has 3 neutrons, which is not very stable, okay? Now, let's go back to regular old hydrogen. Note that the charge is 0. If I take that electron away, hydrogen now has a plus charge, okay? It becomes what we call an ion. And these ions are nothing more than these neutral elements that have either gained or lost electrons, either a positive or a negative charge. If I add 2 electrons, it has a negative charge, okay? The hydrogen has that unique capability where it can lose 1 electron, and then it can gain an extra electron to give you a negative charge, right? We had talked at length about carbon, so let's create carbon. So we need 6 protons. Okay, notice as I add the protons, there are 6 protons. The charge is a +5, so being neutral carbon, it should have 6 protons and 6 electrons, okay? Notice when I bring in another 3rd electron, it goes to the outermost shell because the innermost shell is full now. You can only handle 2. If you recall, that's the first one with hydrogen helium. It can only handle 2 total electrons. So let's continue to add the appropriate number of electrons. We're still at the +2. We still need 1. Okay, so now we have neutral carbon. And normally, the most abundant isotope of carbon was carbon-12. Okay, so we continue to add neutrons, and here we are, the most abundant isotope of carbon is carbon-12. Now, we had talked about carbon-11. Notice you take 1 neutron away, we got carbon-11, which is a little bit unstable, okay? Go back to carbon-12, most stable one. Carbon-13 is also fairly stable. And then we also talked about carbon-14, okay? And in all cases, we did not change what the element was. It still was carbon. We just created, so demonstrated here, we have all the different ions. Some elements have, not ions, excuse me, isotopes. Some elements have, a few couple of isotopes. Carbon has at least 4 that we're aware of. Hydrogen has 3, and they vary depending on the element. Okay. All right. So this tool here would help you out with respect to demonstrating, showing you, or visualizing how protons and neutrons and electrons interplay. Remember that by gaining and losing electrons, if I pull an electron away, I've got a positive charge, okay? And but if it gains electron, I've created a negative charge. Note the count up here in the left corner: protons, neutrons, electrons. Remember, protons are positive, electrons are negative. If I have 6 protons, 6 electrons, I have a neutral charge. The moment I add an electron, I have 1 extra electron, so my net now is a -1. And these are the ions. And you can have a charge, a negative charge, from a -3 to -2, -1. Okay, you can have a positive, from a positive charge from a +1, +2 to a +3. Carbon is very unique because being on, if you look at the position where carbon is, it's in group 4A, Roman numeral IVA, which is 4A. That means there are 4 valence electrons, okay? 4 valence electrons. I got 1 too many electrons. And the outermost shell. Notice this model here of carbon. There are 4 valence electrons. Carbon has the capability, being in the middle, because we're looking for the magical 8, where it would lose all 4, or it can actually pick up 4 more to fill up the outermost shell. But more on that in a bit. Okay, so check the simulation out for you to help you out with the model, with the current model that we have for the atom and the electrons and the neutrons. So anyway, we ended up on this particular page. We had just, let me back it up a little bit, where we had talked about the first 4 energy levels, which correspond to the period on the periodic table, period 1, 2, 3, all the way to 7. And that in the first energy level, which this picture should really be upside down, like an upside down pyramid, if you will, you have 1 orbital, and that's the s orbital, okay? In the second energy level, starting with lithium on the periodic table all the way across the neon, you have the s orbital, but we introduce the p orbital, okay? The third energy level also has the S, also has the P, and then we introduce at this energy level the D orbits. And then the period or level 4, SPD, and then the F orbits come into play. Okay. Now, the confusing part that can occur is these orbitals right here. Notice we are in the 3rd energy level, okay? But these electrons in the d orbit actually come from elements for this in the 3rd level from the 4th period, okay? The mathematics of that, and it starts with element number 21. You have the periodic table, you can see where that is. It is, element 21 is in the 4th energy level, okay? But the d orbitals for element 21 are an energy level 1 less than the period that element is in. So element 21 is in period 4, but its d orbitals are actually in the 3rd energy level, okay? And if it was element, say, number 39, which is on the 5th period energy level, its d orbits would be in the fourth energy level. And that's all due to the mathematics of this quantum mechanic and the orbits that have been determined. The F's down here are actually coming from the period 2 energy levels difference. The D's is 1 energy level, but the F, for example, these F that show up in the 4th period actually come from the elements in the 6th energy level. Okay. And I'll explain some more here, some examples here in a bit. All right, so with that, we come to this periodic table, because what this does is kind of helps you to use the periodic table with respect to writing the electron configuration for the elements. Now, why do we want to learn the electron configuration of these elements? Because that's going to give us insight as to why certain elements want to gain electrons and why other elements want to lose electrons, okay? Now, the takeaway here for this is the blue in the far left. Think of those as the S elements. Okay? And so we have the energy levels 1, 2, 3, 4, 5, 6, and 7. Okay. And so the first 2 columns, think of those as the S elements. If you look at the on the yellow, okay, notice that there are 1, 2, 3, 4, 5, and 6 columns. Think of these guys in the yellow as the P elements, right? Now keep in mind, for S electrons, we can put 2 electrons, okay? So the first column will represent the S1 electron. Second column would be the S2, saying those elements have 2 electrons, S1. Starting with the yellow, the first column would be P1, P2, P3, P4, P5, and then P6. That is the superscript. That superscript represents the number of electrons. So there are 6 columns in the yellow. Look at the D. In the D, we have 5 d orbits, and each one can handle 2 electrons. So there are a total of 10 electrons for the D orbits, right? So we can start from here, D1, and go across to D10, okay? Now for us in Chem 130, it's going to be sequential. So I'll show you a graph or a table where it's not going to be sequentially. So D1, D2, D3, okay, etc. But we are for 130 to be sequential. Now, when we get down here, the F's, it's like F1 down to F14. It's 14 columns, all right? And that's why we say, think of those elements down here, the lanthanides and the actinides, as the F elements. As I was mentioning earlier, element number 21, which is this one, that's where the D's come into play. And so it's in the 4th period, but those D's would only be, would actually be in the 3D, 3 energy level. And for Y, it would be in the 4D, etc. Okay, because the D orbits are actually 1 energy level less than the energy level that they're in. And the same is true for these guys, because this is 6 and 7. So it will start off with 4F and 5F, respectively. Okay, but we're not going to do a lot of the D's and the F. You know, they might show up as maybe extra credit type of question, but our emphasis would be mostly in the S and the P. Okay, and one more here. And so if we look at the electron configuration for, let's do sodium. Okay, so I tend to want to use a periodic table, because the periodic table would, at very quickly, I can, knowing the position where the element is, I can very quickly write down the electron configuration. For example, let's take a look at sodium. Sodium is right here, okay? And so we got 1, 2, and 3. So sodium is in the third energy level, okay? So that means that the 1 energy level and the 2 energy level will be full. So we can very quickly write 1s, because we know there's only one s orbit in the first energy level. And we can write 2s and 2p, because in the second energy level, only the s and the p appear, okay? And then since sodium is in the third, we can do just a 3, and then furthermore, it's in the s elements right here, okay? So it's an S, and furthermore, it's in the first column, very first column of the S element, so we can do a 1. So we're already there. So now we know that sodium has 11 electrons, right? Total. And based on this position, I already fill out the outermost shell. That's like that. So now what's left is to simply come back and just add the maximum number of electrons that each orbit can handle. Okay. And so you can see, add up the subscripts, and guess what? That's 11. Okay. So that is the electron configuration for sodium using the periodic table and its position right away, and then realizing breaking up each group into the S, P, D, and F. Okay. Now, furthermore, this third energy level, that is the most outermost energy level for sodium. That is what we call the valence electron. There's one sole electron in the valence shell. Okay. So if you look at the group number on top of that group, you see the Roman numeral 1A. Well, that Roman numeral 1A applies to everybody in that group. Everybody in that group down the column has 1 valence electron. Where they differ is the energy. For example, potassium would have its valence electron would be in the 4s1. And down the road, 4s1, 5s1, exactly. Okay. All right. Now let's do the sodium. So it's 1s2, 2s2, 2p6, and then finally the last one, 3s1. Okay. All right. Let's do oxygen. Well, let's find oxygen. Oxygen's right here. Okay. Oxygen is in the second energy level. Okay, so that tells us for O that the 1s and 2s and 2p are the orbitals that we have to concern ourselves with. Find oxygen, look in the yellow group, which is the P, count the columns from left to right, 1, 2, 3, 4. It is in the fourth column in the P group. So you can very quickly put a 4 into P, 2P4, okay? The rest now you just fill out. So that's, the S has 2 and 2, so we got 8, 9, 10. I mean, excuse me, 8. So we got 4, 2, and 2, which is 8, which is the number of electrons that oxygen has, okay? So see how quick we filled that out? All right, look at the group that oxygen's in. It is in Roman numeral 4. Excuse me, 6. A, okay? That tells you that there are 6 valence electrons. Of those 6, 2 of them are in the s orbit and the 4 are in the p orbit, okay? That is the outermost shell. So here we have, oh, There we go. Okay. All right, let's do calcium. Clear out. Calcium is right here. And we have 1, 2, 3, and 4. Okay. And so calcium is in the 4th energy period, energy level. So that means that 1s is there, the 2s is there, the 2p is there, the 3s is there, and the 3p. Okay. Now you might see the 3d there, but I'll bring because remember the d is also in the 3rd energy level, but I'll say something about that. And then we got the 4s. All right, first of all, calcium is in the 2nd column of the S. 2nd column of the S, so we can put a T. Okay. Now, with respect to the D, you don't have to worry about the D until you actually get to element number 21. So the D's are not even involved here. Okay. Then we got the P, which is full at 6, the S, 3S at 2, the 2P is 6, 2S is 2, and 1S is 2. See how quickly we did that? Okay. Yeah. 4S2. Now, if you look at calcium, it's in the Roman numeral 2A. That is, tells you that there are 2 valence electrons in the outermost shell, okay, which happen to be in the 4th energy level, because that's the period that calcium is in. All right, now let's do chlorine. Well, we're going to need to identify chlorine. Chlorine is right here, okay? And the period 1, 2, and 3. Chlorine is in the 3rd energy level, okay? So again, we have the 1s, the 2s, the 2p, okay? The 3s, okay? You don't have to worry about the 3D. Why? Again, because we're not even, and we're not dealing with element number 21. We're not there yet. So we got 3P, all right? Now count the columns where chlorine is, starting for the yellow, for the P element. So we go 1, 2, 3, 4, and 5, all right? So we put a 5 there, and that's 3P5. Obviously, the S is full, the 2P6 is full, the 2S2 is full, and the 1S2 is full. Okay. If you look at the group number that chlorine is in, it is in group number 567A, which tells you that there are 5 valence electrons for chlorine, 5 of them. And they're in the 3rd energy level. Okay. Okay. Now, with that being said, see how we did that. Now, here's the thing. If you recall, with respect to metals losing and gaining electrons, which one is it? Oh, sorry, I just saw your message. Okay, sorry. Let me back up. I just saw the message. The question was 1s2. Okay, 1s2 would be helium. Okay, let me show you the next slide. Maybe that would answer your question. Okay, a little bit better. Okay, check out this slide here. Okay, these are the electron configurations for each of the elements. Okay, what I stated here, these were the D's, remember the D's, okay? And I stated that we're gonna do from D1 sequentially to D10. Because you can see that they hop around. Okay, but K130 will go from D1 to D2. The same is true for the F. Also notice that we are in 1, 2, 3, and 4, that for element number 21, which is right here, it is in fourth energy level, but the D, its D orbitals come out in the third energy level, okay? And the F's come out with 2 energy levels less than the period that it's in. So this is period number 6 and number 7, okay? So for this element right here, the F orbits are 4F1, and then we shoot it down to F415. We're going to just call this 5. There's a reason that happens. We'll just call that 5 for the next one. Notice there's 2 energy levels. So the question earlier was, well, how did I get to 1s2? Well, that's helium, okay? Helium's way over here on the far right. Helium only has 2 electrons, okay? And so it is in the first energy level. So hydrogen's up here in the corner, left corner. That's hydrogen, that's helium. And then this one right here is lithium. And then beryllium. So follow along with the periodic table so you can see the elements. Okay, so that is the sequence. So as we go to P, what was the other question was, how do we get 3P6? Well, let's take a look at, here's the third energy level right here. We went across way over here, okay? 6 columns. Remember the ones in yellow are the P electrons. There's P1, P2, P3, P4, P5, P6. The number in front is the energy level, okay? So notice in P1 column, that very first column, which is group 3A. 3A, everybody in 3A has 3 valence electrons, okay? 2 of them are in the S orbit and 1 of them is in the P orbit. And everybody down that column has a P1, 2P1, 3P1, 4P1, 5P1, etc. Okay. All right. Do you see that, Ollie? Anna, Karen, do you guys see that from this slide? Okay. Yeah. And so that's why I prefer to use the periodic table, because you can, just by knowing where it's at on the periodic table and what period it's at, and keep it in mind, here's the S elements, here's the P elements, and here's the D elements, okay? And you can very quickly write the electron configuration, or you can follow the table down here in the bottom, okay? Because that is the sequence of how to add these electrons. Because when you build the electrons, you got to start at the first energy level and fill that up, and then just move up to the second. When you're in the second, there are 2 orbitals, the S and the P. Well, S is a lower energy a little bit than the P. So you fill the S first, then you fill the P. And then if you have D in that level, you fill the D. And then if you have F, you fill the F. The sequence is S, P, D, and F, okay? And of course, obviously the energy level 1, you fill that first, then 2, then 3, then 4, then 5. All right. All right, so let me back it up a little bit. I think this slide here really shows the whole thing with respect to electron configuration involved the elements. And just keep in mind that these are special, but we're going to keep it sequential, D1 to D4, okay? All right. So let's say, let's say you were doing element number 21, which is right there, okay? Well, being number 21, it looks like all the levels are full. 1, 2, 3, and 4 are full, and then you end up with 3D1. Okay, so you write down 1s2, okay, 2s2, 2p6, and then you start the third energy level with 3s2, 3p6, okay, and then you wrap around to the fourth because it is in the fourth energy level. So you go across the 4s2, and then if you count the number of exponents there, that's only 20. This is number 21. So that last electron goes into the d orbit, specifically the 3d1, okay? And that is element number 21. If we go across, all the way across to zinc, this is zinc right here, then we simply put 3d10, okay? And if we went back to, that would be number 31, which is right here, then we're back to the fourth energy level, and then we got 4p1. And that would be the electron configuration for that. So you see how it goes? So as you go across the periodic table, when you hit the Ds, the number drops by 1, and you hit the D electrons, and then you go D1 to D10. And then as you go across, when you go back into the P elements, then you go back up in that energy level it's in, and then P1, P2, P3, P4, whichever, whatever column it's at. Okay. All right. Now, let's back it up a little bit. And now those were electron configurations that we just done for sodium, oxygen, calcium, and chlorine. Now, if you recall, I said, put this in long-term memory. Metals, okay, all metals, they tend to lose or gain electrons. Remember what I said about all metals? They lose or gain. They lose, exactly. Okay. And let me explain here why. Let's take a look at sodium, which is right here. Sodium is a metal. Okay. And we just did the electron configuration here. And the valence electron all by itself is a 3s1. Okay. All right. Now keep in mind, in the 3s1, in the 3 level, we have the 3p energy level and the 3d, but those are not being used because we're dealing with sodium. So we're, it's sodium. There's not enough electrons to fill those other orbits. And from an energy perspective, it would take a lot of energy to put in 6 p's in there, and even more so 10 electrons in there. It just would not work at all. It's just extremely unstable. Okay. And so it would not, metals don't want to fill up electrons because it just be unstable for them. So what do? They rather give up that electron, the outermost electron, the valence shell. There's only one of them. So from an energy perspective, it dumps it, gets rid of it. Okay. And in doing so, sodium now has 10 electrons. And its new configuration, electron configuration, is this. And because it lost an electron, guess what? Now has a net positive charge. And this creates an ion. Okay, that's the sodium that you put on your French fries, the sodium ion. It is the difference between the sodium element and the sodium ion is one tiny little electron. Now the valence shell for the ion has 8 electrons on their outermost shell. It obtained that happy 8, if you will. That octet rule has been fulfilled for sodium metal by losing the electron. That outermost shell is empty now, okay? It's empty, and the next shell in, which is in the second energy level, has 8 electrons around it. Now, take it one step more. When I compare the sodium ion with the sodium, let me restate that. when I compare the radius, the size of the sodium element with respect to the sodium ion, which would you predict to be bigger, the element or the ion? What can you deduce based on what I just explained about the size, the radius of the sodium element, which has 3 energy levels now, and it loses an electron? What do you think has happened to the diameter of the ion? Did it get bigger? Who's bigger, the ion or the element? Yeah, which is smaller, yes. The element, not quite. The ion, oh, excuse me, the smaller the ion would be correct. I misread the answer there. Yeah. Well, why? Let's think about this now. Let me clear up this mess I got here. Okay. Look at the element. The element has 3 energy. Let me draw it this way. Okay, let's say it's a sodium nucleus. It's got 1, 2, 3 energy levels. 1, 2, and 3 for the sodium. Okay. Now, and it's got 1 little electron in the outermost shell. Now the ion now only has 2. Why? Because the outermost electron is gone. And so now its radius is smaller. So the ion is smaller in diameter, in size, than the element because it lost that valence electron. Okay? Plus, it made it more stable because now it's got 8 valence electrons around. Now, let's take a look at a nonmetal. What did I say about nonmetals? Do they want to lose or gain electrons? Remember what I said? Nonmetals want to not lose, metals want to lose. So if metals lose, what do you think the nonmetals? They want to gain electrons. Okay, and let me show you why. Okay, let's look at chlorine. Its outermost shell has 7 valence electrons. Okay, this is the outermost shell. Okay, the P can handle 6, remember? 6. So it has room to pick up 1 more electron. All right, because the P right now as the element, there's only 5. So it can pick up 6. So when it does that, its electron configuration now is 3p6. Okay. And by picking up an electron, now it has a net charge of negative. Okay. So it picked up an electron. Now look at the valence electrons now, whereas before there were 7 for the ion, now there are 8. Here's that octet rule has been fulfilled. And so when metals lose that outermost electron, the new octet is 8 to form the positive ion. Those are metals. And when nonmetals, they have room to pick up electrons. Okay, it's from an energy perspective, it's a lot more favorable to gain 1 electron than it is to try to lose these 7 right there. Okay, so it very readily picks them up. Okay, so that's what happens to chlorine. In fact, everybody in group 7A, that's what happens to them, because everybody in group 7A have 7 valence electrons, and they have room for 1 more. So all of them will want to pick up 1 electron. And in doing so, now they have the same number of electrons as chlorine now has the same number of electrons as argon. Okay, it did not become argon. That's important. but it has the same number of electrons by gaining one. Okay, and the noble gases are very stable. And why they're stable? Because they have the octet rule has been fulfilled. All right. So the electronic configuration, when we draw them out, gives us insight as to why certain things gain metals and certain things lose metals. Now, these guys, we can't really predict as much as for these, the D and the F, like we do for the S elements, because they could have multiple, the metals there can lose more than one electron or two electrons. They can vary by the number, and it's unpredictable. For group 1 and group 2, 100% predictable how many electrons they're going to lose. Everybody in group 1, okay, put this in long-term memory. Everybody in group 1 will always lose one electron, and everybody in group 2 will lose 2 electrons. And that is why you see my periodic table broken up like this, marked up like this, because we're going to talk about it. Here's everybody in group 1. They're going to lose one electron and hence have a +1 charge. Everybody in group 2 will always lose 2 electrons. Okay, so there are 12 elements that you can predict 100% of the time what kind of charge they're going to have when they lose electrons. And then the other 4 are aluminum, zinc, silver, and cadmium. I circled them. Those guys always lose, aluminum always lose 3 electrons, with a ends up with a +3. Zinc always loses a +2 electrons with a +2. Silver always loses 1 with a +1, and cadmium ending up with a +2. So there are 16 elements that you know 100% of the time what their final charge would be when they become ions. That means that all the other metals can vary, okay? Can vary. And so the other aspect is this, when it comes to the nonmetals, we're going to deal mostly, majority of the time with nitrogen and phosphorus. You know, being in group 5, they got room for 3 electrons, so they're going to end up with a -3. Everybody in group 6, they got room for 2 electrons. They're going to end up with a -2. And everybody in group 7 will end up with a -1 charge because they got room for 1 electron, like the example I just did. And those, now you have, you know, 100% of the time for the nonmetals, what kind of charge they will always have. And with that information, when we start putting molecules together, you will be able to put molecules together in the correct ratio, because we're going to look at their charges. And when we put them together, I need to put enough positives together with enough negatives to cancel out. Okay. And to do that, I must know what their charge is, and therefore I can find that out quickly by, again, their position on the periodic table. All right. Okay, we talked about this one, and why your book uses the term happy, but I'll go with it. Okay, noble gases are stable, okay, simply because they have the octet fulfilled, with the exception of helium. Its rule is for helium is a duet, okay? It's a maximum number of electrons it can handle, 2 electrons. But all the other noble gases, that's the last column on the far right, have 8 electrons around it. Therefore, they are very stable, relatively inert, okay? Because that octet has been fulfilled. And it's difficult, it would be difficult, once you got that 8 around you, it's difficult to pull one out. It doesn't mean you can't pull one out. There is, you're able to take one out. But because they're held down tightly by the nucleus, it takes a lot of energy, okay? And difficult also to add electrons, because if they were to add an electron, the only place they can go will be into the next energy level. And that itself is unstable, okay? All right, so that is the octet or the happiness that chemicals are trying to obtain. All right, the valence electrons, as I stated, those are the outermost electrons. That's where all the actions happen in the outermost shell. And the other electrons, they're inside, or those are called the core electrons, and they're full. Not much going on. Okay. And so if we look at phosphorus, for example, okay, you can see its electron configuration is given here. 1s2, 2s2, 2p6, 3s2, 3p3. All right. Phosphorus, the valence electrons are in the third energy level. There are 5 of them. Okay. Phosphorus is in group 5a. Right? So that tells you how many valence electrons it has. Of those 5, 2 of them are in the s orbit, and the other 3 are in the p orbit. Being in group 5, they have room, and they're nonmetals. They have room for 3 electrons because those that p orbital can fit 3 more electrons. So phosphorus will pick up 3 electrons with it, end up with a -3 overall charge. Now, when it's the element, we give it the name as phosphorus. Okay. For nonmetals, we actually change the name. When it becomes an ion, and that is when phosphorus picks up 3 electrons, the name is changed to phosphide. Notice we did chlorine. Chlorine is the element. We dropped the ione and it became chloride. Iodine became iodide. Okay. Phosphorus became phosphide. Oxygen, what do you guys think? Based on that information, what would be the name for the ion oxide of oxygen, which has a -2 charge, okay? Because then it can pick up 2 electrons, but we need to change its name. What would you guess oxygen's new name would be once it becomes an ion? Anybody want to take a guess? I know you know it. Okay. We talked about CO2. Remember the name of CO2? We didn't call that carbon oxygen. What do we call it? Carbon dioxide. And so oxygen, the element, when it becomes the ion, changes its name to oxide. Sulfur becomes sulfide. All right. All right, well, the question here says, well, how many valence electrons? You don't have to memorize them, okay? Because you simply need to go and find out what group it's in on the periodic table. So you have to find it on the periodic table. We'll find that chlorine, okay? You can go to the periodic table and find out that it is in group 7. And so there are 7 valence electrons. And if you don't remember that, then you write out the electron configuration. Here is the valence shell, okay? Beryllium is in group 2A, but if you didn't know that, do the electron configuration and you end up with 1s2s2. And then aluminum is in group 3A, and it has 3 valence electrons, okay? 3 valence electrons. And being a metal, guess what? It's going to lose those 3 valence electrons and have a net charge of a +3 after it's done that. Okay, with respect to the valence electrons, and here the emphasis again is when we're dealing with the A elements, okay, the Roman numeral 1 through 8A. Not so much for the B, where the innermost electrons, they have their own name. We're going to talk about that in the next chapter. But those are the ones that will be labeled earlier with the D elements and the F elements. Those have a variable charge, so we can't really predict. But the other ones we can. And so the number of valence electrons for group 1A is 1, and group 2A is 2, group 3A is 3, etc. Okay, across the periodic table. Only for the A elements. All right, so here the question is, how many valence electrons? Well, again, you can write the electronic configuration for them, okay? Or you can find their position on the periodic table. So strontium, Sr, has 2 valence electrons. It is in group 2A, okay? Bromine, like chlorine, is in group 7A, okay? Notice that. Fluorine, chlorine, bromine, iodine, they all belong to the same group. All of them have 7 valence electrons. They differ in where those 7 valence electrons occupy, and that is a different energy level. Okay. Argon has 8, it's a noble gas. Silicon is like where carbon is, group 4 has 4 valence electrons. We're going to learn that they're put in this group because they have similar reactivity. And they have similar reactivity. Why? Because they share the same number of valence electrons. So everybody in group 1A would behave the same chemically, okay, because they share that one property, and that is all of them have 1 valence electron. And sulfur has 6. Now, I talked at length about this part here as to kind of introduce you to it. It says, why do atoms make compounds? Okay, why do they form bonds? Well, again, the driving force is to have that octet rule fulfilled, to maintain 8 valence electrons around it, or 2. Hydrogen, I keep this in long-term memory. Hydrogen will always want to have 2 electrons around it, like helium, that's the only ones. Everybody else is going to have that magical 8 number. All right, so another further example, I think we talked about this already, introduced it, but we have sodium. Look it up, you can see it has 11 protons and 11 electrons as an atom, as an element, okay? Its electron configuration is 1s2, 2s2, 2p6, 3s2. The valence shell is highlighted there in dark white, okay? It is a metal, and being a metal, it would lose electrons. Remember that. Now, once it loses that 1 electron, now it still has 11 protons. It's still sodium, just a different form of sodium. It is called an ion, but now it has 10 electrons. And so now I had 11 positives, 10 negatives, okay? 10 positives and 10 negatives cancel out. I got 1 positive left over, and that is my chart, positive 1, okay? Its electron configuration now is 2s2, 2p6 is the new outermost shell, is the new valence electron, which has 8, hence it's stable. Okay. Now we do sulfur, we do electron configuration for sulfur. We see it to be 1s2, 2s2, 2p6, and then the valence shell, which is 3s2, 3p6. There are 6 valence electrons for sulfur, okay, because it's in group Roman numeral 6A. It's a nonmetal, it's going to pick up 2 electrons. Why 2? Because it's looking for the 8. And in the p orbit, right now it's got 4. So it's got room for 2. Remember, the p's can handle a maximum of 6. So there's room for 2. So in doing so, it now has a charge. And not only does it charge, we also changed the name to sulfide. It went from sulfur to sulfide. Okay. The electron configuration is now the valence electron configuration is 3s2, but now it's 3p6, okay? 3p6, and the name now has changed to sulfide as the ion. Now, earlier I asked you, okay, sodium atom versus the sodium ion, which one's bigger? Okay, can you make the similar prediction with respect to the atom versus the ion? Okay, which one's bigger as far as the radius? The atom of sulfur atom or sulfide? This is sulfur versus sulfur. Okay, what does your deductive reasoning tell you here? Keep it in mind that it gained 2 electrons here. And over here, it lost 1 electron. Okay, so it made the next valence shell now in a second. But over here, we didn't lose it, the valence shell. It's still in the 3rd energy level. We picked up 3 electrons. So what do you think might be the size of the sulfide versus the sulfur? What do you think is bigger? Okay, we got 2 answers. The sulfide is bigger. You are correct, both of you. Okay, why? Because the 2 electrons went into the p orbit. They're negative charge. Okay, so whereas before we had 4 of them, now you add 2 more negatives, they're going to repel each other. Remember, negatives repel each other. And so the net result is that ion will be bigger. Okay, will be much bigger. We're going to learn that these electrons have a great effect on the structure of the compound and why there are for some certain compounds, there's a certain geometry, and they're all related to these electrons. Keep it in mind, if they're negative, they're going to repel each other. Okay, so they're going to repel each other and try to get in a position where they've maximized their repulsion. So in this scenario, they're asking you to write the electron configuration. Now, don't make the mistake of writing the electron configuration for the atom. So read the question carefully, okay? Because they got a charge here. So these 2, the potassium and potassium ion, with respect to the electron configuration, are not the same. The same is true, okay? So this is potassium, this is nitrogen, and this is magnesium. All of these are the elements, okay? And so therefore they would have different electron configuration. Potassium would have the potassium ion would have -1 electron. The nitrogen, by the way, we have nitrogen, which is the element, but once it gains 3 electrons, it's a non-metal, it will pick up 3 electrons, it's in group 5. Can anybody tell me what the name of this ion would be? Based on what we've been doing right now, as far as naming, we went from chlorine to chloride, oxygen to oxide, sulfur to sulfide. What do you think nitrogen would go name-wise? Anybody want to take a guess at that? You don't have to take a guess. Based on what we've been talking about, you can just extrapolate, and that would be correct. It'd be nitrite, okay? Because that naming is important, because you be down the road, you can be putting together, given the formula of sodium nitrite, okay? And with that name, sodium nitrite, be able to determine or or not determine, but be able to give what that formula is for sodium nitrite. Nitrite will tell you it's an ion. That's good. That is correct. All right, so if we write the electron configuration for the ion, it would be 1s2, 2s2, 2s2, 2p6, 3s2, 3p6. If we were doing potassium, all that would be the same. Okay, except there'd be 4s1 for potassium. Okay, that is the valence electron in group 1. It's going to lose it, and now the new valence shell is in the 3rd energy level, and it has 8 electrons. And it is like, I shouldn't say it's not argon. It has the same number of electrons as argon when potassium becomes potassium ion. Okay. The nitride, okay, is 1s2, 2s2, 2p6. The 2p3 would be nitrogen. Okay, and it has room for 3 electrons. So when you pick up 3 electrons, it now becomes nitrite, and now has the same number of electrons as neon. Okay, and then magnesium will also have the same electron. The magnesium ion will have the same electron configuration, okay, as the nitrite. And in both cases, notice the nonmetal and the metal, they lost and gained electrons, so they have the same electron configuration as a noble gas. Okay. All right. So everybody here, with respect, all these elements are what the driving force here is, again, to be like a noble gas, have the same number of electrons as a noble gas. So they're going to do that by losing or gaining electrons. So everybody in group 1A, metals, will be +1 ions. Group 2A will be +2 ions, and 3A will be +3 ions, okay? And we draw that with the superscript plus, if it's just a 1, you can put +1, or you just put the plus, that's sufficient. It makes no difference if it's +2 or it's 2+, same thing. All right. So like, for example, potassium, you just put the plus, but if you feel comfortable putting +1, that's fine too. Okay, now group 7, we end up with a -1 charge, they're nonmetals. Group 6 will have a -2, and group 5 will have a -3. Okay. Nonmetals want to gain, as I stated. There's the charges. Okay. Tell you what I'm going to do. I need to, let's stop it here. I've got to bring some other stuff, but let's stop it here. We'll complete it next Tuesday. And then jump into chapter 5. We'll probably complete next Tuesday also chapter 5. All right, let's stop the share.